In the fourth session of this week, the fourth week, under static inventory problems under uncertainty, I will be continuing with discussing a number of other say numerical problems. The first we will refer to those numerical examples, because already we have referred to the several kinds of inequality expressions, and we will be discussing all these numerical examples or illustrative examples in such a way that you will come to know the application potential of all these inequality expressions. So that is the first part we will do, and the next important topic I am going to discuss, that is the determination of order quantity when understock cost is estimated per unit basis. So here also in this case we will be using several kinds of inequality expressions, and you will come to know that how these inequality expressions are different from the original inequality expressions the proposed by Chebyshev and Gauss. Now, in all the previous examples, the last two examples, what we have assumed that understock cost that remains fixed. That means there is a situation where, irrespective of the number of units short for a given inventory item, the understock cost they remain same. So that is a fixed understock cost situation. So so this is one case, and we can use all these previously referred to inequality expressions. Now the next example, example 3, illustrative example. Suppose we conclude that the distribution is symmetrical. That means how do you know that the distribution is symmetrical? That means the skewness value is assumed to be 0. That there is no the distribution could be the skewed to the left or the skewed to the right. If you say that the skewness is 0, it means it is perfectly symmetrical. So so you have the information up to gamma 1, and with this information you conclude that the distribution is symmetrical. How to incorporate this information in making the decision? Determination of the order quantity, static inventory problem under uncertainty. Assumption of symmetry means for any demand distribution, f small f z bar plus k is equals to, that means f of z bar minus k for all k. That means this represents probability values. That means z bar is the central point, and on the positive side, that means there is the value z bar plus k, against which the probability is f z bar plus k. And on the other side, that means at the same distance but on the other side, the corresponding value is z bar minus k, and against z bar minus k corresponding probability is f z bar minus k. Now these two probabilities are same. That's why this is referred to as a symmetric distribution, and for all k this condition holds. Is it okay? So this if you remember this condition for all k, that means whatever may be the value of your say random variable with respect to that means your central point is z bar, the deviation from z bar on the positive side or on the negative side. So the corresponding probability is remaining same. So that's why this is referred to as the symmetric distribution. So you remember this condition, and if this condition holds, what you do, this is say one of the inequality expressions we have, inequality, Chebyshev's inequalities expression. So this means this one, that means y minus z bar means z bar minus y. Okay, that's because this is a symmetric distribution, and this means half of probability, the difference, the probability of the difference between y minus z bar greater than or equals to k into s. So this is the original, the Chebyshev's inequality, and this is less than or equals to 1 upon k square multiplied by half. So that's why it is less than or equals to 1 upon 2 k square. So this the change you make, and then for the previous cost equation, with the incorporation of this change in the upper limit, the optimal value of k is given by small k equals to cube root of capital K by Cs. So it was in the original expression when you do not know whether it is symmetric or asymmetric. So use the original expression, that means the equality value, that is 1 upon small k square. So you get a value of cube root of 2k by Cs, but here when you assume the symmetric distribution, symmetric, then the expression for small k changes to cube root of capital K by C to S. Capital K is the stock out cost, fixed stock out cost or under stock cost. The C is the cost of the item, and S is the standard deviation. Is it okay? So with previous set of data, so k equals to, k becomes, small k becomes 3.42, and hence the order quantity is determined as x equals to 50 plus 5 into 3.42. S is 5 we have assumed, and so this becomes 67.1. So as you might have noticed that the values are changing. That means and the values are improving, in the sense that as you get more set of information, so your decision becoming more perfect. Now use there's an example 4. The next example is using the Gauss inequality expression. So the expression number 7 and expression number 8. Okay, these two inequality expressions were proposed by Gauss way back in 1821. How to determine the order quantity? So what you try to do here, base is not the mean, here base is it is the moment, and the notation is capital M0. So how do you express your the order quantity? X is essentially M0 plus KT. Okay, so C into X means C into M0 plus C into K into T. What is T? T is the second moment around mode, plus 4 by 9 into capital K by small k square. So you just refer to expression 7. You will get this one is the equality value is this one, 4 capital K by actually K into probability of going out of stock. So that expression is 4 by 9 small k square. So again you follow the same approach. That means you take the derivative, partial derivative with respect to small k. So this becomes this, and ultimately set it equals to 0. The first derivative you set it equals to 0, and the value of k becomes say cube root of 8 into capital K by 9 CT. If M0 is 47.5, if you remember that we have assumed Z bar is equals to 50 and S equals to 5. That's the data we have assumed. So obviously M0 we have assumed to be 47.5, and then K becomes 3.17. Now obviously you need to calculate T. So you have an expression for t square in terms of say m0, s and z bar. So use those values and that expression for t square to get the value of small t in this case. So please note it down that you need to calculate the value of t separately. So for that there is the expression for t square. Is it okay? That means the second moment around the mode. Okay, so please use that expression. So now when the k is known, so obviously and t is known, so you get the value of x at 47.5 plus 3.17 into 5.59. Is it okay? That means c, that is k, and t value is 5.59. So please check whether you are getting a value of t as 5.59, okay, or not. Okay, so your order quantity is 65.22. So this way you calculate. Now you need to determine t using the equation, as I have already mentioned, that t square equals to a square. That means this is the variance plus m0 minus z bar. So this is 47.5 and z bar is 50. So 47.5 minus 50, 2.5 minus 2.5 square, and a square is 5 square, so 25. So you take the the square root of t square, so you get the value of t. If you use inequality, so expression 8, the optimal value of k is given by this one. Is it okay? That means small k is the fifth root of square root of 64 capital K divided by 25 into C, then the fourth root of t to the power 4. Okay. So this is x equals to m0 k, that means fourth root of t to the power 4. So if m2 is 25, m3 is 125, m4 is 2000 and m0 is 47.5, z bar is 50, t4 is equals to 4.4227 and k is equals to 2.29. So my suggestion is you just assume all these values m2, m3, m4. M0 also is given, z bar is also given. You calculate T4. Okay, so once T4 is known, t to the power 4 is known, then you can calculate, say, fourth root of T4. Is it okay? So t to the power 4. So the k is equals to, you get a value of k equals to 2.29, right? So the optimal order quantity is x equals to 66, right? So you get this value. So the 4 examples we have provided, so please go through them, and we have just used out of say 8 inequality expressions we have given. So we have used just 4 or 5 expressions for inequality expressions, and there could be other numerical problems related to the remaining inequality expressions. So in course of time we will be discussing those inequalities also, like we will be discussing say the under uncertainty problems. That means right now we are discussing static inventory problems under uncertainty, and then in course of time we will be discussing dynamic inventory problems. That means the repeated orders over series of the time periods, but the demand is known with uncertainty. That means, so those cases will be discussing, and for dynamic inventory problems under uncertainty, the same sort of inequalities expressions will be using, but your the problem formulations will be slightly different. So, in course of time we will discuss that part. Right now, what we will be discussing, that is how to determine the order quantity when understock cost is estimated per unit basis. So, this is also a case which you frequently come across. In the previous case, what we have assumed that the understock cost remains fixed. That means irrespective of the number of units short, the understock cost doesn't have much change, and so it remains fixed. But in many cases, the condition or this particular assumption may not hold, and that's why you first check whether you need to calculate or need to estimate the understock cost per unit basis or per outage basis. If you say per outage basis, it means the fixed understock cost. That means just one value will be there irrespective of the number of units short. So, in all the previous cases, we assume that understock cost remains fixed or constant irrespective of the number or amount of shortages. Okay. In many cases of inventory management, the understock cost is estimated per unit basis. That means understock cost varies proportionately with the number of units in shortage. Okay. So, if you have this assumption, how do you formulate the problem? Now, we have been using this notation, that is C subscript U, capital C subscript U, that is understock cost per unit. So, this notation we have used. The total cost expression with X ordering quantity is the unknown, and X, the value of X is to be determined. So, for the given inventory item, the total cost expression or the total relevant cost expression is given by EFX equal to Cx Cu integration x to infinity y minus x Fy dy. So, what is this expression? This is basically the expected number of units short. Y is actually your demand and x is your ordering quantity. So, if say the y varies between x to infinity, obviously there is a shortage because you have x units, whereas your demand is greater than or equals to x up to infinity, and for each the value there is a probability of Fy, probability density function. So, that is why this is the expression y minus x Fy dy integration x to infinity. I am sure that you have understood the meaning of this expression. The cost is minimized when Fx equals to Cu minus C by Cu. That means this is an integral expression, and what you need to do, that means you take the derivative of the integral expressions. So, what the rule you have to follow? The rule you follow, that is essentially the Leibniz rule. Now, we want to find a solution with a distribution free method of analysis. We want to find a solution with a distribution free method of analysis. A set of Chebyshev's inequality expressions we can use in this case under different assumptions. Okay. So, this is the point to be noted. Using one particular inequality expression, we get the following expression for the expected cost. That means here one expression is EFX less than equals to C into Z bar plus KS plus Cu into S into 1 upon K plus 1 upon 2K square plus 1 upon 6KQ K3 K to the power 3. Okay. So, this is the expressions you can get, this is you can use, and the optimal value of K is determined by solving the following equation. You just follow the steps and you just check whether you are getting this the expression or not, and what you get, that means you differentiate, or you take the derivative, first derivative with respect to x of the expression e f x, and ultimately you get this equation. Is it okay? Order 4 in k, small k. So k to the power 4 minus cu by c k square minus cu by c k minus cu by 2c equals to 0. Okay, so this is the constant part. So if z bar equals to 50, s equals to 5, c equals to 5, we have all assumed, cu equals to 50, we find k equals to 3.62, and x equals to 50 plus 5 into 3.62, that is 68.1. So that is the solution, assuming the order size is greater than mean. That means what we are assuming, that we always say that x is z bar plus k into s. That means order quantity is greater than z bar. That means x minus z bar is always positive. Okay, so this is the assumption. If order size x is assumed to be less than z bar, that means what we are assuming, suppose here the z bar is 50, we say that order quantity could be less than 50, so less than z bar. So that assumptions we have right now. So if order size x is assumed to be less than mean z bar, the following expression for E f x is obtained based on Chebyshev's inequality. So E f x less than equals to c into z bar minus ks, okay, plus 2ks cu plus cu into s into 1 upon k plus 1 upon 2k square plus 1 upon 6k cube. So the optimal value of k is given by the positive root of this equation. So again, this is the equation you have to solve, right, to get the positive root of the equation. So this positive root of the equation, when with respect to these values, that means if z bar equals to 50, s equals to 5, c equals to 40, and cu equals to 50. So these values will be specified. So you get a value of k as 1.31, and hence the order quantity x is 43.45. Okay, so this is this way you calculate. That means where the assumption is the order quantity is less than the mean. So here the mean is 50. So what you find here, the order quantity is 43.45, whereas in the previous case what you find that the order quantity is 68.1, that means it is greater than 50. Okay, so the assumption holds. Okay, so this is the procedure. If the demand distribution is assumed to be symmetrical and unimodal, the cost equation is given by this one. That means E f x less than equals to, that means this is expected the total relevant cost when the ordering quantity is x is less than equals to c into z bar minus ks. Here again we are assuming that that the order quantity is less than z bar. So c into z bar minus ks plus 2 cu to k into s, k into s plus 2 by 9 cu into s to 1 upon k plus 1 upon 2k square plus 1 upon 6k cube. So minimization of the cost results in the following equation for k. That means 9 into cu minus c by cu into k to the power 4 minus 2k square minus 2k minus 1 equals to 0. So with the previous data, you just refer to the previous data, that means z bar equals to 50, s equals to 5, c equals to 40 and c equals to 50. What you get? You get the value of k equals to 1.46 and x equals to 42.7. Now the point to be discussed over here, that is what you need to do, first thing, that you will be first you must identify the relevant cost elements. Once these relevant cost elements are there, like in this case, what we are assuming that the purchase cost, unit purchase cost, or the unit production cost is one of the relevant cost elements. And the second important cost element that you have assumed, in the first case we have assumed that it is fixed understock cost. Okay, so you have the formulation. Alternatively, you may assume that that understock cost is to be estimated per unit basis. So that is the different case. So one particular part is the problem formulation related to the fixed understock cost or understock cost per outage. You just note down this particular term. That means cost of understock per outage or fixed understock cost. Cost of understock per unit basis. So these are the two cases, two different sets of formulations. This is point number one. Point number two is that when you assume the demand distribution. Now, for depending on the type of the inventory item you deal with, the demand distribution could be either the discrete demand distribution, or it could be the continuous demand distribution. That means depending on the type of inventory item, either you assume that this is a continuous random variable or the discrete random variable. That is point number two. Point number three is that while you develop the total the relevant cost equation. Now this total relevant cost equation must be written in terms of x. What is x? X is the decision variable. Now here, as it is a static inventory problem, always there will be just one decision variable, that is the ordering quantity. Now in many cases, what you will find that when you refer to say the P system of inventory control or Q systems of inventory control, what you find that always there are at least two parameters in any inventory control systems. So the first one in suppose it's a Q system of inventory control. So in the first case it is Q. That means inventory. That means your say the first parameter is the ordering quantity, and the second parameter is obviously the reorder point. Now the reorder point in this case you can determine, but as it is a static inventory problem, so there is no question of the reorder point. Whereas if you extend it to say the dynamic inventory problem, say under say uncertainty, that means you must determine also along with the order quantity for the Q system of inventory control. That means the continuous review inventory control system, you need to determine so the reorder point. So for the order quantity you will have one expression, and for the reorder point you will have another expression. Now so when you extend the total relevant cost expression for the dynamic inventory problem case, that means order quantity you can determine applying all these say inequality expressions. Similarly, you need to also determine the reorder point, okay, referring to say another say inequality expressions or another cost expression which is dependent on essentially one or more of these inequality expressions. So this is very important. That means what are the even if the cost estimates are not there. Now the fourth important point you remember that even if there is the no reliable cost estimates, can there be any solution? Yes, there can be a solution, but in that case, alternatively, you need to define the service level. So, in course of time, in the subsequent lecture sessions, what we will be referring to? We will be referring to the cost based solution, and if the cost based solution is not feasible, that means the cost estimates are not reliable. So, what you need to do alternatively, you must opt for the service level based solution. So, both the cases we will discuss course of time. Okay. So, thank you.